Hey, hello everyone. My name is Xijun Shi. I'm an assistant professor at Texas State University. It's a great honor to give a talk regarding my research. My research topic is utilization of recycled materials in concrete to promote sustainability. Before I started, I want to thank the organizers for giving me an opportunity to present what I have done in the past in the International Conference on Advances in Construction Materials and Structures. I want to, in particular, thank Dr. Blassen Thomas for the invitation. All right, so for my topic today, I'm going to cover three research projects we have done in Texas. The first one is a textile research project, which we used reclaimed asphalt pavement or recycled asphalt pavement, which is wrapped in concrete as an aggregate replacement. A second research I'm going to present is using scrap tire recycled steel fiber to reinforce cementitious materials. And the third one is a field project that we conducted for Oklahoma DOT. The topic is a long-term performance evaluation of concrete pavements containing recycled concrete aggregate or RCA in Oklahoma in the United States. As you can see, all three projects are related to utilization of recycled materials in concrete to achieve sustainability. All right, so for the first one, as I mentioned, is a textile project on using wrap in concrete. So on this slide, I'm summarizing the common practice of using wrap in our construction materials. I think we all know the most dominating and probably the optimum use of wrap is to use wrap in HMA, hot mix asphalt. However, there are some issues related to these applications. The primary issue is related to the aging of asphalt in the wrap. Because of the aged asphalt, the new mixture, if we put too much wrap, it will become very stiff, and we will have some cracking issues in our asphalt pavements. And also nowadays, especially in hot climates like Texas, we use a lot of modified asphalt binder. If we add too much wrap in modifying to blend with modifying binder, then the blended asphalt binder quality will be low. So that's why most of DOTs in the United States only allow 20 to 30% wrap replacement level in new HMA for the course, for the surface courses. Wrap can also be used in base. However, there's also a restriction, and typically the restriction is about 50%. This is because if we add too much wrap in base, then the pavement will have larger deflections because of the low shear strength of the wrap. And also we know asphalt is a viscoelastic material, and it will experience time temperature dependency. So we will tend to have lots of variations in wrap properties, and also the resulting pavement performance. And also back in old days, we still use lead in our gasoline. so that our wrap aggregates may contain lead, and this can cause leaching problems if we put a wrap directly in the base. Therefore, there are some need in using wrap in concrete in the United States, and I know the wrap concrete applications or wrap concrete research has been very popular in India too. In the United States, there are several funded research projects in the past 10 years. Obviously, in Texas, we had a textile project. In Florida DOT, they also funded a wrap concrete project in around 2012. And the University of Illinois also did a wrap concrete project. And I also know Montana DOT also had a similar project. So for our project, the textile funded project, we collected a lot of wrap from different districts in Texas. So here I'm showing 4 wrap samples were collected. One is from Houston and from Amarillo. Those 2 wraps, as you can see, let me bring my pointer here. As you can see, Houston and Amarillo wrap, they contain bigger aggregate size compared to the other 2 sources we selected, Bryan and San Antonio. They contain mostly intermediate particle size. The gradation of the wrap plays a significant role in our research, as I will show you guys later. So after we collected all the wraps, we did a very extensive material characterization. We did a volumetric properties of the wrap. We measured specific gravity, dry unit weight, and absorption. We also extracted the asphalt from the wrap to measure the binding content. We also use PG grade to quantify the asphalt, the aging degree of the asphalt. And we also did some particle analysis. We did a particle shape properties using the aggregate imaging systems that we developed at Texas A&M University. And finally, we did some stone mineralogy testing using Petrographic Study. On this slide, I'm showing the gradation of the wrap and also the mix design we did. As you can see, as I also mentioned in the previous slide, we have Houston, Amarillo. Those wraps contain a lot of large-sized aggregates, and their gradation was very similar. Their gradation was very similar to the gradation of the virgin coarse aggregate we used in our concrete. For San Antonio and Bryan, the gradation was finer than the coarse aggregate and Amarillo and Houston sources. So they were intermediate particles mostly in the gradation. And we also have our sand plotted here. As you can see, sand is much finer than those coarse aggregates. For our mix design, we only used coarse wrap to replace coarse aggregate by up to 40%. The reason why we did not use any fine aggregate was because fine aggregate reduce a lot concrete workability and strength significantly, and also the asphalt content in fine aggregate is higher than the coarse aggregate, so coarse wrap. So we think those asphalt can be better used in hot mix asphalt, because asphalt is the most valuable component in wrap. So for our mix design, we followed the textile class P, which is a paving mixture. We use 0.4 watt to cementitious ratio. We use 220 pound per cubic yard cementitious material content. And then we also use 20% fly ash to replace the cement on a mass base. And we tested 4 wraps. We use the wrap to replace coarse aggregate at 20 and 40% respectively for different wrap types. I think one significant innovation of our research is that we try to use intermediate particle. We try to use intermediate sized wraps to fill the gap of concrete aggregate gradation to enhance aggregate gradation. So we found the wrap concrete made with wrap containing a significant amount of intermediate size aggregates can be qualified as dense graded mixtures. What we did is that we used shellstone mix design method to evaluate the aggregate optimization by adding those dense graded dense wrap by adding those intermediate wrap aggregates, and we found by adding brine and Santonio wrap, our concrete gradation can be improved, and they were qualified as dense graded mixtures. Then we did some microstructure analysis. We used a microscope to observe thin section specimen to identify the wrap agglomeration in wrap concrete. We were also able to evaluate the L void system, and we were also able to see the ITZ properties under the microscope. Here on the right hand side, we have there is a typical wrap concrete picture on the microscope. As you can see, this is a fine aggregate, which is a sand, and you can see here is a particle of wrap aggregate in concrete. You can clearly see the asphalt layer, and you can also see the porous ITZ, and you can also see the aggregate in the wrap. So the thin section technology is really very effective tool to look at the microstructure of wrap concrete. We also did some crack pattern analysis. What we did is that we manually cracked the wrap concrete under mechanical loading. Then we put the cracked sample in our X-ray CT. Then we were able to see the internal cracking pattern of the samples without fully breaking the specimen. And we also observed the crack pattern under the thin section using the thin section specimens under the microscope observation. Then we also did a lot of conventional mechanical tests based on the ASTM standards. We did a compressive strength, we did a modular elasticity, we did a flexure strength, we also did a split tensile strength. And here are some pictures showing the tests. And we also did some pavement related property tests, including coefficient of soma expansion, Poisson's ratio, and we also evaluated the thermal properties, including the thermal conductivity and the heat capacity of the wrap concrete. Finally, we did some durability tests. We did a free thaw resistance according to ASTM C666. We also did an electric resistivity measurements to infer the permeability of the wrap concrete. We also did an abrasion resistance using 2 methods. One is ASTM 9, and the other is ASTM C944. And finally, we did a ring test to evaluate the cracking potential of the wrapped concrete under restrained drying shrinkage. Because of the time limit, I'm not going to show you guys the detailed results. If you are interested, you can find the results in our papers, which will be listed in the end of my presentation. So here I'm just summarizing the key findings from our textile projects. So for the mechanical properties of wrapped concrete, we found adding wrapping concrete causes reduction in strength and stiffness, and this is a very common finding, also from the previous literature. However, we found such a reduction in strength and stiffness can be more mitigated by controlling wrap quality and also by using the dense gradation mix design. And we also found wrapped concrete properties are correlated very well with the total asphalt volumetric fraction, and so that we can use the asphalt volumetric fraction as a control factor to design wrapped concrete to achieve adequate strength and stiffness. Based on our microstructure analysis and crack pattern study, we found the agglomerated wrap particles are the weak zones in the wrap concrete system, and the asphalt area is also a very weak point in the wrap concrete. And we concluded that asphalt cohesive failing is a primary mechanism for the strength reduction. We also did a durability test to evaluate the wrap concrete with up to 40% coarse wrap replacement. And we found our wrap concrete had a very good freeze-thaw resistance, and the permeability of the wrap concrete is also satisfactory. However, the abrasion resistance and the free shrinkage might be a concern. So here we are proposing that we can use wrap concrete in the bottom left of the two left concrete constructions to avoid the abrasion issues and also the shrinkage issues. And we also provide some guidelines on how to select best quality wrap for concrete applications. So first of all, we want to control the asphalt content. We want to select wrap which has the lowest asphalt content as possible. We also want to limit the number of agglomerated particles. And we also think the gradation of the wrap is very important. We like intermediate particle sized wrap. Our ideal particle size is 9.5 millimeter to 2.36 millimeter. So within this size range, the wrap is likely to have very low amount of agglomerated particles. And also this intermediate size can help us design dense graded wrap concrete, which will have very low strength reduction. So for the previous slides, I'm showing that the traditional or more conventional tests we did for our textile project. And as an extension, we also did a few very innovative tests. The first test I want to introduce is the semicircular bending fracture test that I designed as a part of my PhD work. So as we know, we can use we can use a single edge notched beam specimen to test fracture properties for the 2-parameter fracture model proposed by Dr. Shan. However, the beam specimen is labor intensive and also material intensive to make. Therefore, I developed a much easier method which utilize a CB specimen. So for the ACB samples, the radius is 76 millimeter, and so it is basically a 6-inch radius. So how to it is a 6-inch diameter and a 3-inch radius. So how to make this specimen? It is really simple. All you need to have is a 6 by 12-inch cylinder specimen. Then you can cut the cylinder into half. Then you cut the cylinders into different slices. And for my study, I would discard the top and the bottom slices because there are some potential segregation issues. So with one cylinder specimen, I can fabricate 12 ACB specimens. So I can save a lot of materials, and the material and the specimen fabrication process is also very simple. I tried a 2-notch size. I tried a 38 millimeter notch size, and I also tried 12 millimeter notch size, and I found only 38 millimeter notch size is working. So for my results, I use a method to evaluate wrap concrete containing up to 40% coarse wrap to replace coarse aggregate. So here I'm showing the results here. So for the 2-parameter fracture model, we have 2 parameters. One is a critical stress intensity factor, and the other is critical crack tip opening displacement. And within this, using my CB test, I got those values for the wrap concrete. As you can see, for the first column, it is a control sample without any wrap. For the second column and third column is a wrap concrete samples containing 40% Houston wrap and the 40% Bryan wrap. As you can see, the stress intensity factor are very similar, which means adding wrap in concrete will not cause reduction in at least the stress intensity factor. For the critical crack tip opening displacement, as you can see, adding wrap would significantly increase the critical crack tip opening displacement. And for the fracture energy terms, which is G, F, and G big I, F, as you can see, adding wrap also improves the fracture energy terms. So even adding wrap could reduce strength. We found the fracture properties can be improved or can be equivalent, can be similar to the control specimen. We also, by using those fracture properties, we can also evaluate the ductility of the material. So here I'm introducing a concept which is a material length. It is an indicator of the material's breathiness or ductility. And this value, Q value, material length value, is considered proportional to the size of the fracture process zone for a given material. So a higher value indicates the material is more ductile. As you can see, by adding 40% Bryan wrap, the ductility, the material length of the wrap concrete is improved by about 100% compared to the control specimen. So this test confirms that adding wrap can significantly improve the ductility of the material. We also did a ring test. We used a restrained ring test to infer the cracking resistance of the material under drying shrinkage. As you can see, by adding 100% mortar, wrap mortar, fine wrap in the mortar, we can improve the cracking time of the cement mortar by about 100%. As you can see, for our control mortar, the average cracking time is 8.6 days, but for our wrap mortar, the average cracking time is about 15.6 days. So it's about 100% improvement. So here we are only using mortar sample because concrete samples takes a lot of time to crack. So we develop a smaller sized ring geometry, which enables us to have a much sooner cracking time for the cementitious material. Here I'm also drawing conclusions for the second part of this project. So for the fracture properties, we found wrapped concrete has equivalent fracture toughness compared to the control concrete, and the ductility of the concrete can be improved by adding wrap. And the wrap concrete also has higher fracture energies compared to the control concrete. For the cracking resistant under restrained drying shrinkage, wrap mortar samples developed much lower peak strain, and by adding wrap, the mortar samples also have delayed cracking time. And the possible reasons for the better cracking resistance are due to the lower modulus of the material by adding wrap, and also the higher fracture energies, which we already approved in our fracture tests. We also think the stress relaxation due to the higher viscosity of the material can also be a significant source for the improved cracking resistance. So based on these conclusions, wrap-based cementitious materials are not necessarily inferior materials. That's our conclusion. So for this project, I want to thank Textile and the TTI for providing funding and equipment. I want to thank Dr. Nomokapadei for serving as a PIO for this research project. All right, the second topic I'm going to talk about is a scrap tire recycled steel fiber reinforced cementitious material. So using scrap tire in our civil engineering application has very significant implications for sustainability. Based on a report, about 4.2 million tons of scrap tire were generated in the United States in 2017. The tire waste can be a problem because they are non-biodegradable. Tires are also flammable and can also leach toxic substances into the ground. Currently, scrap tires are burned as a fuel, but some states are prohibited from promoting fuel-related uses for tires. We also we recycle tires in. We try to recycle tires, and one of the major applications of recycled tires is to put the tire waste in civil engineering applications. For example, we can use a ground rubber for asphalt concrete and also for cement concrete as aggregate replacement. During the production of ground rubber, we can extract recycled steel fiber by up to 15% of the total tire waste. So if we do a simple math here, we know we have 4.2 million tons of scrap tire generated in the United States every year. And we know 15% of the tire waste can be recycled steel fiber. So we can produce 0.6563 million tons of recycled steel fiber every year in the United States alone. If we only use 3% by weight in concrete, we can produce 21 million tons of concrete by using those recycled steel fiber. And this volume or this mass is more than 3 times the amount contained in the Hoover Dam. So there is a huge market for using recycled steel fiber in concrete. So for the recycled steel fiber, they are conventionally sold as ready-to-melt steel. So they are very cheap. They can be 10 times cheaper than industry-made steel fiber. And also life cycle assessment studies shows that processing the recycled steel fiber consumes less amount of energy compared to the typical manufactured steel fibers. So people are interested in using recycled steel fiber as a fiber reinforcement in cementitious material. In Europe, there are a few research groups are doing recycled steel fiber concrete research, and their research shows that recycled steel fiber can be as effective as manufactured steel fiber for concrete fiber reinforcement. However, in the United States, there is not too much work being done here in the United States. So the objectives of our research is to conduct a detailed experimental program to characterize different material properties of cement mortar reinforced by locally available recycled steel fiber from scrap tire in the United States. We did a lot of mechanical property tests, including compression tests and split tension tests. We also did fracture properties using the newly developed CB fracture tests. We also used the ring test to assess the cracking resistance of the material under restrained drying shrinkage. Here is a picture showing the fibers from the scrap tire. As you can see, it is actually a mixture of everything, including residual rubber, steel rails, those big pieces still inside of the samples. We also have a lot of steel fibers, as you can see, those same particles, and we also have lots of tile texture in the mixture. After we received the sample, we did not do any additional processing. So we did not separate those other phases from the steel fiber. So what we use is what we received. Then we did a fiber dimension measurements. So the average diameter of the steel fiber in the samples we collected is 0.32 millimeter, and the length is about 14.9 millimeter. And the aspect ratio is 55, which is very normal for steel fiber that being used in concrete. So one of the unique properties of the recycled steel fiber is that we have a lot of residual rubber adhered to the fiber surface. As you can see from the SCM we took, you can see a rubber layer on the surface. So we think the rubbers can have some potential effects on concrete properties. On the one hand, we think the residual rubber increases fiber surface roughnesses, which can provide an improved mechanical bond between the fiber and the matrix. On the other hand, we do not want to have too much rubber because it may alter cement hydration and create weak ITZ. And this can be very similar to the asphalt layer in the wrap concrete. So we determined the rubber content for our recycled steel fiber sample, and we found the residual rubber mass content was about 2.25%, which is very low compared to many other samples in the literature. Then we did a mixed design. As I mentioned, we only did a cement mortar tests. We had some concrete results coming out, but I'm not including them in this presentation. So for our cement mortar, we use a 0.4 water to cement ratio. We use a 2.75 sand to cement ratio, and our fiber content is 1% and 2% by volume. We did not use any chemical or mineral admixtures, and we found our cementitious material had a very good workability, even without adding any water reducer or super plasticizer. Here I'm showing some mechanical properties results. The major findings is that adding those recycled steel fiber did not significantly change the compressive strength and the modular elasticity. However, the split tensile strength of the concrete, of the cement mortar was improved significantly. Here, as you can see, by adding 2% recycled steel fiber, the split tensile strength was improved by 50% at 20 days. And we also find a very similar study in the literature using manufactured steel fiber with a similar size the steel fiber to what we used in our study for the recycled steel fiber. And we found that the split tensile strength improvement for the manufactured steel fiber was only 37%. As noted here, we can achieve 50% improvement. So we believe the recycled steel fiber could have equivalent or even higher fiber reinforcement effect compared to the manufactured steel fiber with similar size and similar dosage. We also had some fracture property test results here. As you can see, by adding fibers, the stress intensive factor, the crack tip opening displacement, and the fracture energies all improved significantly. We also have the cracking resistance results showing here. Again, adding fibers improves the peak strain, and we also have a higher level of the residual strength after cracking, and the cracking time also improved by about 50% compared to the control sample. Here are some conclusions for the mechanical properties. Adding 2% recycled steel fiber shows little effect on the compressive strength and the elastic modulus for the cement mortar. However, we achieved 50% split tensile strength improvement by adding 2% recycled steel fiber. And the reinforcement effect of the recycled steel fiber appears to be comparable or even higher than that of the manufactured steel fiber with similar sizes. And we believe this improvement or equivalent performance was caused by the improved fiber surface roughness due to the residual rubber. For the fracture properties, adding 2% recycled steel fiber increased the stress intensive factor and the critical crack tip opening displacement, and the fracture energy were also improved significantly. For the cracking resistance, adding 2% recycled steel fiber increased the time of cracking of the cement mortar by 50%. And after major cracking, the fiber reinforced mortar sample could still maintain 55% of the pre-crack strain in the steel, and this residual strain is about around 200% higher than that for the control. That is my that is my second topic. My third topic is Oklahoma DOT project. And during that project, we went to Oklahoma and we evaluated the long-term performance of 2 concrete pavement sections containing recycled concrete aggregates. So why do we want to recycle concrete pavements? I know all of us are well aware of the benefits, right? We can achieve economic benefits and we can also achieve environmental benefits. I'm not going to put more explanations here. I'm sure we all know these very well. So by adding RCA, recycled concrete aggregates in concrete, our concrete mixtures will have different material properties. So by adding RCA, the slump effect can be either beneficial or detrimental. By adding RCA, the air content will be increased because the RCA is more porous than nature aggregates. For the abrasion resistant, tensile strength, compressive strength, modular selectivity, flexural strength, and carbonation resistance, by adding RCA, those properties will all be reduced. And by adding RCA, we will also increase the drying shrinkage, creep, chloride penetration, and also thermal expansion. So those are the lab results from the literature review. So what we did is that we went to Oklahoma City in 2017, and we evaluated 2 existing RCA concrete pavement sections in OKC. So a little bit of background about the 2 existing concrete pavements. They contain 100% coarse RCA, and the concrete pavements were built in the 1980s. So by the time we went there, the concrete pavements already had close to 40 years of the service in the field. We have 2 concrete pavement sections. One is JPCP, jointed plain concrete pavements, and the other is CRCP, continuously reinforced concrete pavement. And those 2 sections were never evaluated extensively in the past, so that in that project we had a very unique opportunity to see the long-term performance of those RCA concrete pavement sections in the United States. For the 2 sections, as I mentioned, one is JPCP and the other is CRCP. And the length is about 8 miles for the JPCP and about 6 miles for the CRCP. And the construction time were about 30 to 40 years ago for both sections. And for both sections, we have a control section aligned with that with the RCA section. This is really good news because we can directly compare the performance of the RCA concrete with the control RCA, control concrete pavements. For the base information, for the I-40, which is the JPCP section, it had a soil asphalt base, which was very weak, as I will show you guys in the later slides. And for the CRCP, it was built on a very solid asphalt concrete layer, and the asphalt concrete thickness was 4 inch. So why did the contractors used RCA back in 1980s? Because for I-40, they found the nearest virgin aggregate source was more than 50 miles away. So to achieve economical benefits, they decided to recycle the aggregates from the old concrete pavements, and they turned out to save 63,000 tons of virgin aggregates and saved $0.8 million back in that time. And for the project construction, everything went well. They were able to produce satisfied Class A concrete using 100% RCA. And the reason why they demolished the old concrete pavements was because they found there was significant decracking issues. So to avoid decracking issues from reoccurring, they decided to use reduced aggregate size, and it turned out the approach was effective. For the I-35, there was not too much additional information. We only know that the concrete was, the old concrete where the RCA was from was built in 1960, and the new RCA concrete was built in 1988. And after 20 years, Oklahoma DOT also went to the field section to see the performance, and they did not see any significant distress of the RCA concrete. Then in 2017, we went to Oklahoma City to see the field performance of the RCA concrete after about 40 years service in the field. We saw a lot of longitudinal cracks on the I-40, but we did not see any decracking on I-40. Remember, I-40 was reconstructed due to the decracking issues in the 1980s. For the I-35, everything looked fine, and we also caught we also extract some specimens from the fields, and we found the I-40, the base material was weak. It is asphalt treated soil base, as you can see. It's pretty weak. But for the I-35, the base was asphalt concrete. As you can see, the bonding between the asphalt and the RCA concrete was still good, as you can see from the sample here. And then we did some FWD work. We evaluated equivalent thickness, base coefficient of friction, differential energy, and load transfer efficiency based on some series we developed at Texas A&M University. For our results, I did not show the results. I'm just here. I'm just showing the conclusions. As you can see, for the I-35 JPCP, the RCA section showed lower performance than the control. The equivalent thickness was lower, the base coefficient of friction was lower, and the differential energy for the RCA was also higher than control. For the CRCP section, however, the performance between the RCA and control sample was comparable. Both of the sections, both the control and the RCA sections, had a similar equivalent thickness and the base coefficient of friction. But for the RCA section, it still had a higher differential energy, but the performance was really good. We also had a survey data from Oklahoma DOT, and the survey data were collected by Oklahoma DOT on July 10th, 2017. So we got a international roughness index data. We also had a 14 and a punch out data for the RCA sections and control sections. As you can see, the data had the same conclusion as from our FWD results. As you can see, RCA section had a lower performance compared to the control section. The RCA section had a higher international roughness index. It also had higher faulting value compared to the control. For the CRCP, however, the performance was very comparable between the RCA and the control. The international roughness index was very similar between the control and the RCA. Control had a higher patching area, but RCA has higher amount of punch out. We also did mechanical properties using the pores we obtained in the fields. The major conclusion that RCA concrete has lower modulus elasticity and split tensile strength. But we did find something very interesting in that for the I-40, RCA concrete had higher compressive strength than control specimen. But for the I-35, the RCA section had a lower compressive strength compared to its control specimen. We also did a thin section observation using microscope, and we can clearly see the reclaimed mortar here. As you can see, the color is gray. And we also see the cracks propagate through the reclaimed mortar. So that's why we concluded that the reclaimed mortar is a weak zone. So if we want to control RCA concrete properties, we want to limit reclaimed mortar content in the RCA sample. It is very similar to what we want to do for our wrap concrete. We want to control the asphalt content. Here we want to control the reclaimed mortar content. So the general findings from Oklahoma concrete pavements for the RCA concrete, it has reduced modulus elasticity and reduced the tensile strength, but we did find an increase in compressive strength for the I-35 for the I-40 sections. For the reclaimed mortar, we believe it is a primarily weak zone, and the cracks can easily pass through the reclaimed mortar. And for the RCA field sections, we found the field section had lower performance for the JPCP, but for the CRCP, the performance was comparable with the control specimen, section. We concluded the good performance of RCA CRCP was due to the stronger base. Remember, for the RCA CRCP, it was built on asphalt concrete base, which was much stronger than the soil base for the JPCP section. We also think using CRCP, the pavement type will also help the concrete pavements containing RCA. The steel rebar can help protect base from erosion, which is very important for the RCA concrete because our slab is less stiffer compared to the control slab. So that's why we need to make sure the base is protected by using the steel. So finally, I also want to make an acknowledgement for this RCA study. The research was sponsored by the Oklahoma DOT on the project 2278. Again, Dr. Anil Mukhopadhyay from TTI served as a PI, and I was a student working on the project. And Dr. Dan Zollinger helped with the field investigation. And we also want to thank Oklahoma DOT staff for helping us during the field tests. And also we want to thank the nationwide experts for providing feedback on the use of RCA in concrete. Finally, I'm listing some of the publications we made upon finishing the projects for the wrap concrete. The list is here. For the recycled steel fiber concrete, the list is here. And also I have 2 papers published for the RCA concrete. Thank you so much. This is my final slides. If you have any questions, feel free to send me in an email, and I'm also open to any questions for the Q&A section. Thank you so much.